And I'm kind of sick and tired of this tree width stuff, so I'm going to skip the last two parts of the chapter. But this last section, 773, in fact, deals with a beautiful result of Baker, which is a very nice technique for getting approximation algorithm for planar graphs. I'm not going to follow very closely the presentation in the book, at least in the beginning. I'm going to present it in my own way, and then later on I would go back and maybe cover some of the results that I didn't mention. Okay, so the first building block, I would like to speak about the planar separator theorem, which we already mentioned. Right, so the planar separator says that if we have a graph, right, G is a graph, planar graph, namely planar graph, a graph can draw in the plane, planar graph, and you know, all the regular platitude applies, planar graph, connected, because the not connected case is not interesting, with n vertices, then there exists, then one can compute a set of square root n vertices a set S such that G minus S is disconnected and every connected component you know, has at most 2/3 of n vertices. And instead of 2/3, you can choose any constant you want, essentially. This doesn't really matter. So this is a beautiful theorem due to Slater and Tarjan. And I'm not going to prove it because it requires some work and it's not directly related. What we need is something slightly weaker. So let me do the lemma. If the diameter, let's say diameter, why not? If the diameter of G is smaller than R, then the graph has a planar separator with vertices. Okay, and okay, so intuitively this proves the above theorem if the diameter of the graph is square root n, right? And the proof is easy once you've seen it once. And the nice thing is also it's demonstrates very nicely where planarity is playing a game. So you take a vertex V of the graph, G V of the V vertex of the graph, vertex of the graph, and you start the BFS, right? So think about the BFS. This is V. Think about the BFS as being drawn. You know, the graph is drawn on the plane and you just draw the edges that belongs to the tree, right? And you stop as soon as, you know, you just do the BFS tree, so you get the tree, right? Sorted, you know, rooted at this node V. An important thing is that the length of every path from V to any vertex in the graph is at most R, because the diameter of the graph is at most R. Okay. So now, what's the next step? The next step is, and this is really where things get a bit weird, and you kind of have to get used to the idea. Think about taking this tree. Think about the plane as think about in fact taking instead of drawing this tree on a plane. Okay, think that you drew it on an orange, right, on a sphere, right? You can definitely take this drawing and put it on a sphere, right? And now you're going to take a knife and you're going to cut the edges of the tree, right? So, you cut, and of course the surface of the sphere, right, now becomes something which is, let's think that the sphere was made of rubber. It's just a piece of rubber, right? And you can stretch it, right? You can put it on the plane and stretch it so it looks like a plane. And now what happened is that this 3T, right, every edge now have two copies, right? Every, an edge have a one side and the other side, right? So if I take this cut sphere and I draw it on the plane, T becomes in fact a polygon, right? Every edge, E and E prime, right? E would have some copy, and then some later on there would be another copy, right? Maybe this is a copy E prime. Notice that the vertex V here, right? This vertex V might appear here now several times, here and here and here, right? If you know some topology, this is something, this kind of stuff sometimes is called the schema. But for our purposes, all we care about is the fact that we found a polygon, right? That, essentially what we just say is that essentially we are saying that the complement of a tree in the plane, when you draw a tree in the plane, the complement essentially looks like a polygon, right? Now, the important thing about polygons, and here I'm not going to prove it formally because it requires quite a bit of work, is that it can be triangulated, right? You can just add edges such that every face is a triangle, right? And the number of faces is going to be, because of planarity and Euler formula, it's going to be proportional to the number of, initial vertices in the graph. So you're going to get O of n triangles, right? Now, the trick is now to look on the dual graph, right? In every vertex of this triangle, you now put a vertex, right? And you connect two vertices if they have a common diagonal, right? So you get this tree, okay? Now the important thing is, and this is not the edge of this tree, the important thing about trees is that we know that they have a separator vertex, right? We proved that last lecture. So there is a vertex such that if I cut it, cut the trees in balanced way. But in fact, this tree is balanced. This tree is tree regular. So it's not tree regular. It's the degree of a vertex is at most 3 because every triangle has at most 3 edges. So in fact, there is an edge which is a separator, right? And this edge of a separator has the property that each side of it, the tree that remains, when you remove this orange edge, is at most 2/3 of the mass of the tree. Okay. And we're not even recording this, right? I forgot it. Good news, I am recording it. Okay, so cutting this edge would break the polygon into two pieces that are of balanced way. And in fact, instead of cutting this edge, let me remember the diagonal, right? The diagonal that crosses this edge. There is a unique such diagonal, this fat green edge, right? Let's go back to the tree. It means that there are two vertices that if I put an edge between them, it breaks the plane into two regions, and those two regions have roughly the same number of vertices and edges on both sides, right? You wanted to prove it formally, but let's not go into that because it's not very interesting, right? The only thing I want you to realize is that look on, so we know that the number of polygons, number of triangles in the two pieces is roughly the same, right? If I introduce this edge back, this edge is this edge, and you do the calculations and you can show easily that the number of triangles is the same, right? And this also implies the number of vertices is the same, up to constant factor. So it is essentially what happens is that this edge, together with the tree, breaks the plane into those two regions. In fact, let's follow the separator edge, right? You can go from the separator edge back to V, and from V back to the other end of this thing. So we get a cycle, right? And this cycle breaks the graph into those two pieces which have roughly the same number of vertices. So the cycle is a separator. If you take all the vertices of the cycle, it's a separator and break the graph into two pieces of similar size. And the important thing to remember is that the diameter of the original graph was at most r, so the distance, the length of the path from those two leaf nodes to V is going to be at most r, right? So this cycle is going to be this separating cycle is of length at most 2r plus 1, right? So this readily implies the theorem. Again, I'm skipping a bit of the low-level details, but you shouldn't care too much, okay? So we get immediately this lemma that says that if the diameter is r, then there is a separator of size of r that breaks the graph in a balanced way. Okay, and this immediately implies, if this is true, if we have a separator of size r, right, now we can apply this theorem to the two pieces recursively, right, and so on. So we get the decomposition, right? So we get the tree decomposition, right? So we readily get the following result, theorem, right? A planar graph of diameter r at most r has tree width of r. And again, I'm kind of, hand waving the proof, but the proof is essentially you take the separator and you recurse on the two pieces, right? When you duplicate the separator vertices into the two sub-problems, and then the only thing you have to do, which we saw before, you have to kind of, in the recursive sub-problem, you're getting a piece of a subplanar graph, and now you need to use the idea that, first you have to be, there are some low-level details that one needs to be very careful about them, but the more important thing is that you need to observe is that at some point you need to start cutting, instead of just breaking the graph in separate it to be two pieces of similar size, you have to separate the separator vertices, right? So there are a lot of low-level details, but the rule of thumb is that if you can have a separator of size t, then you immediately get, and this is a hereditary property, then this immediately implies that, the tree width of the graph is at most t, right, and I guess that one needs to be maybe somewhat careful here because of what? Yeah, no, I don't think it's, right, yes. I think there's some low-level details you have to be careful about, but, since I'm not trying to be very precise here, let's leave it at that. I think it's good enough. Okay, so why is this interesting? Okay, so this is interesting because we know how to solve various problems on bounded tree width with fixed parameter tractable time, right? Think about independent set, for example. Right. If I have a graph, then we can compute the independent, we can approximate the independent set we can in fact compute the independent set of a graph if the graph has bounded tree-width in fixed parameter tractable time. So it's natural now to ask to do it for a planar graph. So if the planar graph has bounded diameter, then by what I just showed we are done, because it has bounded tree-width and we can compute the tree-width and we are all good. But if on the other hand it's not a bounded, if it's, if the diameter is large, what do we do then, right? And in this case, what we are going to do, we're going to get an approximation, right? And the idea is that we are willing to sacrifice something, right? We're willing to lose something, but still get a decent solution, right? So the key observation, which is going to be very important, is that let's think again about this planar graph, and we have a vertex, and we start doing BFS, and now I have these layers of the BFS, right? And it's in fact more convenient to think about it explicitly as the BFS. And now the trick is that think about taking every delta level of this BFS tree. So this is distance delta, right? Well, delta is going to be some parameter. Okay. Now, the key idea is that this is a ladder, right? Every delta level we take of the BFS tree. And now the trick is that we are going to shift it, right? So think about delta, 2 delta, 3 delta, right? And I'm going to add a shift. So 3 delta plus alpha, where alpha is going to be some parameter. 2 delta plus alpha, delta plus alpha, and in fact it will become also alpha, right? So we're going to have this ladder every delta level, and the natural way to think about it is that I pick alpha randomly from the range 0 to delta minus 1. Right? I'm picking randomly an integer number in this range, and that will be my shift, right? And the idea is that if you think about it, is that the probability of a vertex to be in one of those chosen level is going to be only 1 over delta. So we're going to lose 1 over delta fraction of what we care about in the graph, right? And if we don't care about much, then we are good to go, right? Okay, so why is this interesting, right? So this is interesting because let's randomly pick, think about the independent set, right? So we have a planar graph. In a planar graph, there is always a vertex of degree 5, at most 5. This follows directly from Euler formula. So that means, in particular, the planar graph can be colored using 6 colors, right? You take this vertex of degree 5, you remove it, you color the remaining graph, and then you put this vertex back, and there are 5 colors you have to avoid, the neighboring color, then you choose a 6th color. So this is the easy proof that planar graphs are 6 colorable. You can work somewhat harder and prove that 5 colors are enough, and of course you can work much harder and prove that 4 colors are enough. Right. This is the famous 4-color theorem, but for our purposes 6 colors is enough for our purposes, because it says that one of the colors must be at least n over 6 of the vertices. Right. So the independent set of the graph is of size at least n over 6. So a constant fraction of the graph is independent set. So in particular, if I lose, I lose n over delta vertices, this is much smaller than the size of the independent set, right? So in particular, what I'm going to do, I'm going to take the planar graph, choose this alpha randomly, and then just delete all the vertices that are on the ladder. Right? If I do that, then in expectation or in average, whatever you want to do, what I will get is that the size, G minus the ladder, the independent set in it is going to be still quite large, okay, you know, it's going to be at least, you know, the independent set of the original graph minus n over delta, which is not much if delta is sufficiently large. Okay, so now we're left with the task that, you know, we have this, now we have this portion of the planar graph between two, you know, those two, I delta and I delta, I plus 1 delta plus alpha, right? We have this graph and we have this planar graph in between those two things, right? And now we want to find the largest independent set part here, right? But the important thing is that, you know, the top of this tree, right? The top of this tree, this whole region, this is just a BFS tree, right? This is just a connected subtree of the original planar graph. So I can just take all the edges of this tree and just contract them, right? So this whole tree, if I take G and I contract all the vertices in the red subtree into a vertex, what's going to happen is that I get a you know, let's call it H, right? J and contract H, right? So this top of the tree is going to become one big vertex. To remind you, contraction doesn't change planarity, right? So we're going to have this vortex that swallowed all the top part of the graph. And now we deleted, to remind you, we deleted the bottom level and the top level of this ladder, right? So this blue graph, you can think about it as being something like that, right? This is the blue graph. And then there is the green boundary where we cut, right? On the outside, right? So this is the graph we have, right? But the important thing to remember is that, you know, this was distance delta in the distance delta in the layers of the BFS, so which means that in this new planar graph that we are looking at, the distance from the red vertex to any vertex in this graph is at most r, right? In particular, the diameter of this graph is at most 2r, because you can go from any vertex back to the red root and so on. So this bizarro planar graph, let's call it K, right, have diameter at most, what is diameter? At most 2 delta. Diameter of K is at most 2 delta, right? And as such, we can compute its largest independent set in time, which is, you know, some function of, you know, its tree width. So the tree width of K is at most of delta, right? And we can compute as such the independent set of K in time, which is, you know, some horrible function of the parameter delta, and, you know, linear time, in fact, for planar graphs, because planar graphs, everything can be done in linear time, essentially, right? Oh, well, this is tree width, so we can do it in, we can do it in linear time. We saw how to do that. Okay, so why is this, this is good? Because this, let's go back to our tree, right? We cut it in those randomly shifted levels. For every one of those layers in between the cuts, we computed the largest independent set. We deleted the ladders of the, you know, you know, those delta levels of the tree. And for every one of those pieces, we computed the largest independent set, and then we just take the union, right? And, you know, overall, clearly the running time we get is going to be, as I just said, you know, some horrible function of delta, some f of delta. I don't even care exactly what times n. For each one of those pieces, we have to do it for each piece, so overall the running time is going to be like that, right? And what we get an independent set of size. It's not going to be the optimum independent set, right? The optimum, it's going to be larger than the optimum independent set. But we are losing something, right? What we are losing, well, n minus delta, right? Because we are losing all lengths of the level. Here I'm using n over delta because of the random shifting in expectation we are losing n over delta. If you don't like expectation, just check each one of the choices of the shift. One of them must be smaller equal than average, which is n over delta. Okay, so the independent set is at most net. In particular, if I take delta to be, you know, what should it be? 6 over epsilon, right? If I do that, then the size of the independent set is going to be, well, the independent set is at least, this is at least n over 6, right? Because the independent set of a planar graph is always at least n over 6. So this is going to be, you know, opt minus opt epsilon opt, right? So we get 1 minus epsilon approximation. So we got 1 minus epsilon approximation to the maximum size independent set. This is a very nice result due to Baker. And it can be used for other problems. And for some reason, the book doesn't mention the independent set problem. I don't know why. I kind of like it better. And of course, this is the original application, in fact, of Baker. But let me now go to what the book mentions.